And welcome to Acids and Bases Part 2. And we have some very interesting follow-up from what we did before, or if you're just joining us, some really interesting information to cover. Happy to see those of you that are here and learning this material because, again, this is one of the highest yield topics on test day. You will definitely see acids and bases on your test. So now what we're going to do is take pH and solve questions related to pH, learn how to do that consistently no matter what gets thrown at you. All right, so that's our #1 goal for the next hour. So let's talk about titrations: strong acid, strong base titrations, and weak acid, strong base titrations. And we're going to look at them at 3 different points. We're going to look at them where we start, when we're halfway through, and when we are at the equivalence point, which means we're done. All right, so let's look at our strong acid, strong base, HCl and NaOH. Let's say we start off with 30 equivalents of HCl. We are going to be making water and good old sodium chloride, our friend table salt. When we start out, we haven't added any base yet, so let's say we have 30 equivalents of HCl. We have no equivalents of sodium chloride because we haven't made any yet. If we're working with a weak acid, it's going to be the same thing. We're going to start with 30 equivalents of the acid, none of the salt. Now in this case we're writing out HA because most of our weak acids have big long names. So we'll just call it A for the acid part. H is for the proton that's going to pop on and off. But the same thing is there. We've got just the acid, just the H+. Now, the initial pH for a strong acid is really easy because where we're starting is that the initial HCl concentration, monoprotic acid, yes, I did pay attention to which one it is, just equals the H+ concentration. It's a strong acid. It completely dissociates. Our weak acid is a little bit trickier. With our weak acid, it's only partially dissociated, so we have to use the value of Ka, since Ka is just what kind of constant. I know you know this. Tell me down in the chat. What kind of constant is Ka when we're talking about a weak acid? And it's hiding, yeah, it's a KeQ. So we can use the KeQ for that dissociation, and in that process we can solve for H+ by setting up algebraically, isolating H+, plugging and chugging the numbers. When we are halfway through, we're going to have 15 equivalents of acid, because we've, by definition, used up 15 of them, and we'll have made 15 equivalents of sodium chloride. Now, the NaCl is inert. We've already determined that since this is a strong acid, this is an inert conjugate base. And the HCl concentration halfway equals the H+ concentration. Halfway through our weak titration, we still have 15 equivalents of our weak acid. We've made 15 equivalents of our salt. But we're going to use the Henderson-Hasselbalch equation to calculate this. Now, I know many of you just had a very bad reaction when I said that. We're going to see how straightforward this is to use. It's much more friendly to calculations than you might think once you understand what it is. All right, how about the equivalence point? Well, at the equivalence point, we've used up all our acid, and everything has turned into sodium chloride. Guess what? Our pH is going to be based on the fact that the acid's neutralized. Since it's strong and strong, it's got to be pH 7. On the other hand, with our weak acid, same thing, no acid left. It's all in the form of salt, but the only thing we know is because it's a weak acid, it's got to be greater than 7. Without a lot of really fancy dancing around, we don't know the exact number, and that's very unlikely to come up on test day other than knowing it's got to be above pH 7. So let's do something realistic with this. Let's determine the pH of a 10 to the negative third molar HCl solution. Okay. Now, what do we know about HCl that's going to make this really easy to do? This is the very straightforward one. What's true of HCl? It's a strong acid and it's monoprotic. Excellent. So what do we know about the pH of this solution? If the solution is 10 to the minus third in HCl, what do we know about its H plus concentration? It's exactly the same. There you go, Ashley. And what do we know about manipulating logarithms? Since pH is negative log of the H plus concentration, very good. It's got to be pH 3. Okay, cool. Now, this is the trickier one, finding the pH of a 10 to the negative third acetic acid solution. I mentioned this in the last hour. I will say it again. Acetic acid you must know. You don't need to know its Ka or its pKa, but you do need to know the formula of it and that it's a weak acid. So to do this, we have to use what we know about the Ka. And just like any other equilibrium constant, it's products over reactants. This is splitting up into these two things. Okay, then we plug in what we know. We know that its pKa is 5, therefore its Ka must be the anti-log of that. Don't be afraid of the word anti-log. It just means if this is the pKa, its Ka is 10 to the negative fifth. This, our HA, some amount of it dissociates. That amount is called X. So we put in X for each of these and we get X squared. The concentration of what we put in is 10 to the minus third. Now it's really 10 to the minus third minus X. Why do we ignore the X in the denominator? Why isn't that written as 10 to the minus third minus X? Exactly, Ashley. It's so small, it's negligible. So we can ignore it. And that's wonderful because now we are not doing a quadratic equation. Trust me, none of us want to be doing that. Now we just solve. X squared is going to equal 10 to the minus 8th. What's the square root of 10 to the minus 8th? Exactly, Alyssa. You got it, Alyssa. You nailed it. So what's the square root of 10 to the minus 8th? And this is easy. If you're struggling with this, it's easier than you think. As long as you have an even exponent, your life is super easy. Yeah, you just cut it in half. That's the rule. You just cut it in half, you get 10 to the minus 4th, and that's our H plus concentration. Are we done? No. What do we want? We want the pH. pH is negative log of the H plus concentration. There you go. You're already anticipating our pH is 4. Excellent. All right, third. So we have our initial concentration, our half point, and now we're going to do our equivalent point. The pH of a 10 to the negative, oh, sorry, we're not doing that one. We're doing ammonia. I'm getting ahead of myself. I'm imagining a problem we're going to do in a moment. We're going to do the same thing with ammonia. Now for this, Kb, same thing. It's a base if it's accepted a proton and split water. So this is our reaction. B becomes Hb plus OH minus. And we go through the exact same process. Its pKb is 5, so its Kb is 10 to the minus 5th. X for each of these, 10 to the minus 3rd. We solve. X equals 10 to the minus 4th. So what's our pH of this solution? Very good, Brandon. Very good, Sarah Beth. That will give us the pOH. And we have to subtract from 14 to get the pH. Make sure you answer the question that's being asked. Very nice. So notice these two calculations, very, very similar except for that final step. Everything else about them was the same. Next, half equivalence point. What's the pH of a 10 to the negative 3rd solution at the half equivalent point with NaOH? Strong acid, strong base. So what do we know about our H plus concentration halfway through our titration? What's happened to that? Half used up. So it's going to now be 10 to the minus 3 over 2. Okay, that's not bad. That means it's 5 times 10 to the minus 4th. That's just manipulating exponents. That's something you do need to be able to do quickly for the MCAT. If you struggle with it, practice. And here's the trick. This was 0.5 times 10 to the minus third, right? We made the 0.5 bigger to be a 5, so the 10 to the minus third has to get smaller, meaning further from 0. They always go opposite directions. Okay, if that's our H plus concentration, what's the pH? If this were 1 times 10 to the minus fourth, our pH would be 4. Since our H plus is higher, tell me what that means about our pH. It's got to be lower than 4. Brandon and Ashley are all over it. But it's not as low as 3, because that would be 1 times 10 to the negative 3. Mariah's got it. Alicia's got it. It's going to be approximately 3.5. And again, for the MCAT, good enough. Let's do the same thing for B. This is the pH of our 10 to the minus third acetate, acetic acid, at the half equivalence point. Notice there's more room to write this out, isn't there? That's because it's a little more complex. So it's a buffer solution. We'll use Henderson-Hasselbalch. Henderson-Hasselbalch is a good friend of yours, because here's how it's set up. It says the pH of a buffer, and a buffer is defined as something that has both a weak acid and the conjugate base of that weak acid, or a weak base and the conjugate acid of that weak base. It's got the two of them in solution together. And the pH of that solution equals the pKa plus the log of the conjugate base over the acid. Our acid in this case is acetic acid. Our conjugate base is the acetate with the H taken off. The logarithm of this is going to be easier than you think. So our pKa, if pKa equals 5, we don't even have to manipulate that. That's just a 5, right? If we are at the half equivalence point, what is true of the conjugate base and the acid? What's true of them? That's a 1-to-1 ratio. Okay, so if it's 1 over 1, if they're the same concentration, what is inside this parentheses? And what's log 1? Log 1 is 0. So when we are at the half equivalence point, when the conjugate acid and the conjugate base are the same concentration, the pH equals the pKa. And in that case, it means it's 5. That's the first thing we're going to learn about Henderson-Hasselbalch. We're going to come back to it. You're really going to come to appreciate it, I promise you. So for our ammonia, we're going to do the same thing, aren't we? And it turns out Henderson-Hasselbalch has a version for bases. And it looks exactly the same. The PaOH equals the pKb times the log of the conjugate acid over the original base. Well, we're given our pKb. Half equivalence point, that's 1. This whole term goes to 0. What's the answer to C? Brandon is not going to let me fool him. And how did Brandon come up with 9? Well, our POH equals 5. And what do we need to remember to do? Yes, exactly. Excellent. Molly, Mariah, Sarah Beth, you've got to subtract it from 14. Excellent. You are not being fooled by these. I love it. Okay, good job. Now let's do our end point. And some of these we'll be able to determine exactly, some not so much. So our equivalent point pH of our strong acid titrated with strong base. Anybody know the answer to this? Yeah, it's 7. What we've done is we've gotten to water. Our sodium chloride is inert. By definition, our H plus is 10 to the minus 7th, and our pH equals 7. That was the quick one. Now we've got B, the equivalence point of our acetic acid titrated with a strong base. Ashley's already there. Excellent. Remember, we're combining acetic acid with sodium hydroxide. We're making some water and the sodium acetate salt. And the only thing we know is that that's inert That's a weak base. And water is a teeny tiny amount of H+. Who wins out? Our base wins out, and Ashley and Sarah Beth are exactly right. Our pH is going to be greater than 7. Now, based on that alone, tell me what you think the answer to C is. Ashley's using those critical reasoning skills. I absolutely love it. Yep, you've all nailed it. Since we're working the opposite direction, it's exactly the opposite thought process, and our pH is going to be less than 7. Remember, you're not asked to calculate these exact pHs, but understanding where they end up, excellent job on that. Okay. Now, let's play around with ammonia some more. Ammonia is another favorite of the PCAT for a lot of different reasons, but let's play with it and see what we can learn about it. And we're going to use the Henderson-Hasselbalch equation without even really knowing too much about it. So pKa, and this is important, always pay attention to whether you're given the pKa or the pKb. We're given the pKa of ammonium, and it's ammonium because it has NH4 and it has a plus. So that takes ammonia, turns it into ammonium. Its pKa is 9.26, and it's asking us to solve for the ratio of ammonia, the conjugate base, over NH4 plus, the acid. So what do we know when these two are equal? What did we learn from Henderson-Hasselbalch about those when they were equal? The pH equals a pKa, exactly. So which solution has a ratio, a 1-to-1 ratio of ammonia to ammonium? Yeah, exactly. There's our 1-to-1 ratio. Okay, but what if we were to increase the ammonia to being 10 times as much as the NH4+. Well, if this is 10 times bigger, if the ammonia is 10 times bigger than the ammonium, what does that ratio turn into? What number does it become? 10 to 1, okay? And if we put that into a fraction, it's just 10 over 1. And what's log 10 over 1? It's 1. Excellent. And if we're going to add that to the pKa, what does that mean happens to our pH? Exactly. It goes up to 10.26. What if it goes up to a factor of 100 over 1? It's going to go up to 11.26. Okay. Now, let's go the other way. What has happened if the pH has dropped by a unit? If the pH went from 9.26 to 8.26? What's happened? Ashley says we've increased the acid. Yeah, now we have a 1-to-10 ratio. Excellent. And if we've dropped 2 pH units, what's our ratio now? Think in terms of exponents. Yeah, it's 1 to 100. It's 10 to the second. Excellent. That's what Henderson-Hasselbalch tells you. That's what this equation is about. So when you see this, pH equals pKa plus log of the conjugate base over the acid, any fear of Henderson-Hasselbalch anymore? Any worries about what this equation is telling you? Told you, you'd get to be friends with this guy. Or I guess it's 2 guys probably. Now that's silly. One of them might have been a gal, so you can slap my wrist again for that one. Yeah, this is a very, very user-friendly equation once you understand what it's telling you. Very, very nice. All right, that was so much fun. Let's do it again. This direction. Let's use our pKa of acetic acid. It's actually more correctly 4.74. All right, that's fine, close enough. What's the pH of each of these? Now, what is the easiest one to do? Out of all 5 solutions, Which one is the simplest one to solve for? 3, because what's our ratio of base to acid there? 1 to 1, and what's the correct answer for number 3? 4.74. That's about as easy as it gets. Okay, how about row 2? What's our actual ratio there? 1 to 10. And if it's 1 over 10, does our pH go up or down? Very good. It's going to go down. Excellent, Emma. And in fact, if we go to 1 over 100, it goes down even further, yes? All right, what about the other way? Row 4, what's our ratio there? 10 to 1. And so what's going to happen to our pH? It's going to go up by 1 to 5.7. Look at this. And what have we got for our final entry in the chart? That's right. And you know, Sergey's making a really excellent point for us that even if you don't remember top or bottom, okay, think about this. If we have increased, this is our base and this is our acid. If we have more base, okay, should our pH go up or down? Tell me down there in the chat. If we have more base, should our pH go up or down? Yeah, it should go up. And if we have more acid, what should happen to our base? Not to our base, to our pH? It should go down. Henderson-Hasselbalch is a pushover, it turns out. All right, very, very nice. I feel scores on the MCAT cranking themselves up right now. I don't know about you, but this is actually pretty exciting. So now let's do some exercises. Let's work through a couple different steps here and see what we can work out on these problems. So let's start with problem A. We're looking for the pH of a solution that is 0.1 molar nitric acid over 0.1 molar nitrate. Now, there's some information in the corner. How does that information help us? What's important about that? Yeah, we can determine the pKa's. Excellent. What does it tell us about the nitric acid? It's big. It's a strong acid. And if it's a strong acid, how do we figure out the pH? First of all, how do we determine the H+ concentration? How do we determine the H+ concentration? What's the only thing contributing H+ in this case? Only the strong acid. Very good, Ashley. Yeah, in this case, the nitrate isn't really contributing anything. We don't even really care it's there. So, what is the H+ concentration of solution A? And this is one I don't want you to overthink. Brandon's got it. Nope. Think about it. It's given to us right there because it's a strong acid. Very good, Sharifa. Think about this. This is different than a buffer. Brandon and Sharifa have it. With a strong acid, the H+ is exactly the same as the acid that we dissolved in solution. This is why strong acids and strong bases are not used for buffers. They have no buffering capacity. They are, what you see is what you get as long as it is a strong acid or strong base. Okay? So that's the first thing, is don't be fooled. It only donates H+. Yeah, it's what we're given. H+ is 10 to the minus 1 and pH equals 1. So I know we learned all this really fun stuff to do, but you don't use it at all when it's a strong acid. And remember, your strong acids, you should know them. Nitric acid, hydrochloric acid, sulfuric acid. There's a few others, hypochloric, hydrobromic, hydroiodic. You do need to know your list of them because the great thing is if you know your strong acids, any other acid has to be a weak acid. It's actually kind of cool. All right, let's go on to problem B. B says we have HNO2 with NO2 minus. Now, is this a strong acid? Yes, Ms., that is correct. You are absolutely correct, Ms. They are inverse. Now, this is a weak acid, and how do we know it's a weak acid? There are two ways to know it's a weak acid, by the way. The Ka, okay, and why does the Ka tell us that it's a weak acid? What is it about the Ka that makes us certain it's a weak acid? Less than 1. Exactly. Remember, 1 is your cutoff point for weak versus strong. All right. The other way we know that it's a weak acid, it's not on the list of strong acids. Okay, good enough. But for what we're doing, we actually need that Ka value, don't we? So when we look at problem B, what do we notice about our HNO2 and our NO2 minus? What do we notice about those two? One-to-one ratio, okay? So how do we calculate the pH? What do we know about the pH for B? The pH equals the pKa, all right? The pKa, it's not an even number, is it? So what do we have to do with that number? If we look at 4.5 times 10 to the minus 4, what's the largest that the pKa could be? What's the number? Yeah, we're going to work down below 4, aren't we? 4 is going to be the highest, and we know it's slightly less than 4, but above 3. And exactly, Brenda, Alicia, and Ashley have got it already. 4 is the highest it can be. It's got to be less, but it's not going to be as small as 3, because 3 would be 1 times 10 to the negative third. 3.5, 3.6, good enough. Good enough for the MCAT. You will never be asked to do a calculation on pH that's more exact than that. Okay, what about C? HClO. Strong or weak? Let's start there. It's definitely weak. Do we have any conjugate base hanging out with it? Do we have a conjugate base? No. So how do we figure out the pH of this? Can't use Henderson-Hasselbalch here, can we? Because we have, yes, Ashley, very good. We're going to set up the KEQ equation. That's exactly right. And these always solve the same way. So we're going to set it up to where the number we're given, 3.2 times 10 to the negative 8th, well, this is going to split up into H plus and ClO minus. Okay, that's supposed to be an H plus, and it looks like, I'm not sure what it looks like. There we go. So each of them, for every X amount of this that dissociates, we get X of these and X of these. This is going to be 0.01 minus X, but that X is so teeny tiny we don't care about it. Now we have to do a little bit of math, and we have to be careful about it, because 3.2 times 10 to the minus 8th times 10 to the minus 2, what is our exponent going to be when we multiply that out? 10 to the negative 10th, that's right, make sure of that. Okay, so X squared is 3 times 10 to the minus 10th. Is that 3 really going to be a big deal? What's the square root of 3? It's between 1 and 2, right? So we don't even really have to worry about that. What's the square root of 10 to the minus 10th? You'll notice we do a lot of estimating here, don't we? Yeah, it's 10 to the minus 5th, somewhere around that. 1 or 2 times 10 to the minus 5th. 1.7 times 10 to the minus 5th. Once again, that's going to be close enough that on test day, you'll be able to pick out the right answer from that. Very nice. Question D. Question D sure looks like question B, doesn't it? What's the big difference with question D? It's a different ratio. Do we need to redo anything, or can we work from pre-existing work? What do we do now? What's the best way to approach this? Okay, so do we have more acid or do we have more base? Yeah, we have more base, so what's our answer going to be for question D? Yeah, it's going to be around 4.6-ish. Very nice. All right, and then E, last big finish here. Let's see what we've got here. We have ammonia, ammonium, and ammonia. So what's our ratio here? There we go. Yeah, be very careful there. Very careful with your decimal places. It's 10 to 1, and which do we have more of? Acid or base? Acid, right? The NH4 plus is our acid. The NH3 is our base. And what's our pKa? What's our pKa for this? We're starting with 10 to the minus 10th. So we know it's got to be above or below 10. We add 1 to the pKa, but we got to get the pKa. So we've got 5.6 times 10 to the minus 10th. So what's the first thing that we do with that minus 10? Yeah, we say it's going to be less than that. It's got to be above 9. Excellent. And yeah, roughly around 9.5. But what do we have to do to that 9.5 now? Add or subtract? Very good. And our final number is going to be, Alicia's there already. I'm so pleased. Anybody else got a number for me? Yeah, about 8.4. Yep, there you go. Look at this. Look how well you're managing this. Excellent. Okay, now let's talk about buffers. I mentioned this before. With a buffer, we take, in this case, acetic acid, and we make up a solution of acetic acid. Then we go over to the shelf, and we take a bottle of sodium acetate, and we add the same number of equivalents of the conjugate base as we do the conjugate acid. So this is not a reaction. This is something we're setting up in the lab. Once again, I'm trying to set it up correctly so the other people in the lab don't yell at me. So if I have a buffer with 10,000 equivalents of acetate and 10,000 equivalents of acetic acid, my pH equals my pKa. It's 1 to 1. Exactly, Ms. So what happens to this particular solution if I add an additional 10 equivalents of H plus to the 1,000 each that are already there? Is that going to mess up my ratio very much at all? No, it's barely going to budge it at all. What we're going to be looking at is 4.74 plus the log of 990 over 1,010, which is 99 over 101. I mean, seriously, is this really going to be changing anything? No, because the idea is, even if we've added a little bit more H plus, all it does is combine with a little teeny tiny amount of the acetate, shift very, very slightly this direction, and if we're, say using this for cell culture, none of our cells die because they're still at this happy pH they want to be at. All right. What if we're being a little chintzy? We don't use quite so much acetic acid, quite so much acetate. We've used 100 equivalents of each. Now we're still starting at pH 4.74 because the absolute amount doesn't actually matter. What does matter is the ratio. But now we're going to add 10 equivalents. Is this going to have much of an impact on what's going on here? What's going to happen when we add 10 equivalents to 100? So now we're looking at a 10% shift, right? Is it going to stay the same? A 10% shift, what are you thinking? Big swing, little swing. Let's look at some numbers. Yeah, now we're looking at 90 over 110, which is 9 over 11. And you know what's going to happen? We're going to drop our pH by about, notice it's a 10% difference. We dropped it by about a 1/10 of a point. Oh, that's consistent, isn't it? But now, what if I'm the lab assistant, I read the recipe wrong, and I made it up with only 10 equivalents of acetate and 10 equivalents of acid? We throw in 10 equivalents of H+. What's going to happen then? Bigger swing? How much of a swing? What's going to happen to all of my acetate? Yeah, it's going to be bad, Sarah Beth says. Yeah, this is why I don't work as a lab assistant anymore. Yeah, we use up all of our acetate. It's all eaten up, and our pH drops like a rock because now our pH is determined by actually 20 equivalents of acetic acid being in solution. Yeah, so this is how buffers work. If you have a strong enough a high enough concentration of your acid and conjugate base, it'll eat up any little bits of acid or base that happen to wander in and drop into your solution. But they won't buffer against really big accidents, like if your other lab tech walks over and spills an entire beaker of acid in. Guess what? Your cell culture just died. Sorry. But that's the idea behind buffers. Small amounts of acid and base really don't change your pH. Excellent. Now, in addition to buffers, let's come back to the world of titrations again. How do you know your titration's done? How do you know you've reached your equivalence point? By a color change if you're using an indicator. Now, really, truly, the best way is to use a pH meter. That's most accurate. But for an awful lot of titrations, an indicator will work just fine. Well, what is an indicator? Well, right here we have a picture of methyl red. And methyl red is a weak acid. And how do we know it's a weak acid? Well, right here we have a carboxylic acid. And here we have a dissociated carboxylic acid. Notice the difference there? And it seems like a silly little thing, but all you have to do is remove that H+, and it changes the light that is absorbed and reflected by this molecule. So when the H+ is on it, when it's in its acid form, it's red. When the H+ is removed, when it's in the conjugate base form, it's yellow. And guess where? Let's think about this. Where would it change color? Okay. We have a 1 molar solution, and we have 3 possible pHs, 4.2, 5.2, and 6.2. And its pKa is 5.2. What's going to be true at pH 5.2? And you're right, Ashley, it can be either organic acid or base. What's going to happen at pH 5.2? What does our friend Henderson Hasselbalch tell us? The pH equals the pKa. That's right. Okay, and if the pH equals the pKa, what happens to our concentration of red and yellow? What happens to our concentration of red and yellow? They're equal. And now let's go back to grade school. What color is it? If it's half red and half yellow, yeah, it's going to be orange. That's exactly right. Okay? What if we are at pH 4.2? What's happened if we've gone up to pH 4.2? What's happened to our ratio? Or sorry, gone down to pH 4.2. Our ratio changes by how much? Very good, Sarah Beth. Sarah Beth went straight to the ratio. So what's decreased? Be more specific. Sarah was specific. I want the rest of you to be specific as well. Ashley says 1 to 10. I'm assuming, I'm making an assumption about that. Very good, Ms. Very good, Emma. 10 is the acid. Yeah, okay. So that's gone 1 to 10. So that means we've got more of what color? What color is winning out now? Yeah, it's going to be red. And what happens if we go to pH 6.2? Now what ratio do we have to have? Yeah, it's the other way around. We've got 10 times as much base, and what color is our solution? Very good, Ms. Yeah, it's going to turn yellow. That's how indicators work. And you pick an indicator that changes color at about the pH that you're looking for. That's the idea behind it. And I want to show you one more thing about this that's really cool. This is nothing different than our friend Le Chatelier. Because if we increase our concentration of acid, which way does our equilibrium shift? Shifts that way, so it picks up more yellow color, doesn't it? Yeah, and if you start out all yellow, it's going to shift back this way and turn more orangey reddish. So what we're learning from Henderson Hasselbalch and what we're learning from Le Chatelier are perfectly consistent. So the color change occurs when the pH solution, that's when you're going to go from yellow to orange. Then if you keep going, it'll turn more red. If you start out red, going back the other way, that pKa is where it's going to turn to orange and then further to yellow. Do you have to use exactly the pKa as your endpoint pH? No. As long as you don't need to go more than half a point to a point beyond. Exactly, Ashley, plus or minus 1 point around it. Excellent. So you choose an indicator with a pKa near where you want to be. Okay, that's what we already talked about. Okay, what do we have here? We have a very short passage. What I would like to do is I'm going to give you 1 minute to read this passage. So 1 minute to go through and read it. And then I believe that we have, how about if we go slightly longer than 1 minute? There are 5 questions. I'm going to give you a total of 6 minutes. You don't have to finish everything, but see how far you can get. 6 minutes to read, do questions 1 through 5, as many of them as you can get through, and then we'll review. Have fun. So tell me what you thought about 6 minutes to run through a very short paragraph passage and then to work out the questions. What were you thinking about that amount of time? Good, bad, comfortable, still working on it, so you're not typing in the chat? Sarah Beth says she thought it was pretty good. 6 for the 6. I like that, Sarah Beth. Clearly some of you are still working, and that's okay. There's 5 questions in that amount of time. Hey, it works out, Sarah Beth. All right, let's see what we've got going on. Let's start with the passage and look at the information that we're given here. Our student was given a flask with 25 mils of an aqueous solution of ammonia. We're given the pKb, important to notice that, of unknown concentration. Aha! So we're going to figure that out. The student was asked to determine the concentration of the solution by titrating it against a standard 0.1 molar aqueous what kind of solution? What's important about this solution? A strong acid. Excellent. That was placed in a burette. The student added 2 drops of indicator to the solution and titrated it against the HCl. Experimental temperature was 25 degrees C. We like that. The student noticed that 40 milliliters of the HCl solution was needed to reach the equivalence point, and then table 1 shows the pH ranges. Now, let's take a look at our first question. Question 1. The student determined the concentration of the ammonia solution to be closest to, oh, and you know what I need to find? I need to find our pole. I forgot to bring that up. There it is. Okay. So let me clear this for you. There you go. You can fill your answers in as we go. What formula did we use for question 1? This is one that we went over in Acids and Bases 1. And it's the classic solution that we use. Yes, N sub A, V sub A equals N sub B, V sub B. We plug our numbers in and we rearrange, and notice that the normality of our base, since our acid is 40 and our base is 25 milliliters, the normality of the base has to be higher than the normality of our acid. Has to be. Okay? And when we do our math, we're going to get 0.15. Okay? Remember, the inverse relationship can often help you make a shortcut. Okay? Let's look at our second question. Upon addition of 20 milliliters to the flask, which of the following was most likely true of the solution? Okay. So how much is 20 milliliters? Why is that number so significant? Is it the equivalence point? What's that 20 milliliters equal to? Yeah, it's the half equivalence point. So if we're at the half equivalence point, that means that the pH equals the pKa for our ammonia. Aha! And if the pH equals the pKa, is it possible for C or D to be true? Nope. And since it's a base, is its pH going to be high or low? It's going to be high simply because it's basic. That alone would be enough to tell us. All right, excellent. Question number 3. At the equivalence point, the number of chloride ions in the flask solution was closest to the following. Now, how do we figure out chloride? Well, chloride all comes from the HCl. And if we've got 0.1 molar HCl, what do we have to have? Right? We've got to have the same molarity, but they want the number of ions. And I apologize for moving the pole around. I'm trying to make sure you can see the numbers. We got to remember Avogadro's number, right? That's at 6 times 10 to the 23rd. Now, this is a little easier than it looks because it's 6 times 40 gives us 240. Then we add up our exponents. We get 10 to the negative 19th. 240 times 10 to the minus 19th. We bring that down to 2.4. We make that smaller, so our exponent gets higher. We moved it 2 positions. So it's 10 to the 21st. And we're all across the board here. If you need to, grab a screenshot of this because I want to make sure that we get to questions 4 and 5. And by the way, what do you do with question 3 on test day? Especially when you see the Avogadro's number. What would be a really good, smart thing to do? Skip it. Absolutely. Come back to it. All right, question number 4. The pH of the titrant was equal to which of the following? What do they mean by titrant? Is that like a tyrant? I don't think so. Yeah, it's the HCl. So the HCl was 10th molar. 10 to the minus 1. 10 to the minus 1, what's its pH? Its pH is 1. Yep. Okay, and then the final question, which indicator was our best choice? Our indicator, well, let's see. If we look at, I'm going to jump us back and very, very briefly take a look at our passage. There it is, and show you a couple things about it. There's our curve. There's where we end up. Look at what fits beautifully into our scale. What's the correct answer here? The correct answer is our friend, methyl red. And what color are we going to end up with? What color do we end up with? It's actually going to be slightly past it, down into the red. All right, very nice job on this. You've learned a ton of information about acids and bases, especially if you've been in both sessions, and it has been a lot of fun to work with you on this. So, quick, what things do you need to make sure you know for test day? You need to know how to convert your pH or your pKa, your logarithms, your Henderson-Hasselbalch, your strong acids. What equation for titrations is always going to be your first choice? The one that we used just a minute or two ago? Nope, for titrations, if you want the 3 out of 4, N sub A, V sub A equals N sub B, V sub B. There you go. You've got all sorts of information at your fingertips. All right. Have a wonderful rest of your evening. There's some biochem coming up, and I don't remember what the next one is, but there's a list coming up. It's been a lot of fun to teach you. Have a great rest of your day.